Electrical circuit breaker BOCB explained step by step in this video. 1. What is a BOCB? A bulk oil circuit breaker uses a large volume of insulating oil both to extinguish the arc when contacts separate and to insulate live parts from earth, dead tank design. It's a traditional high-voltage breaker type used in substations. 2 main components. Quick overview. 1. Tank. Steel GI holds the bulk insulating oil and is usually at earth potential, dead tank. 2. Moving and fixed contacts, current path that opens closes. Contacts sit submerged in oil. 3. Operating mechanism, spring, hydraulic or pneumatic mechanism to open close the contacts on command. 4. Arc chamber interrupter region, where the arc forms, the oil and geometry help quench it. 5. Insulating oil, transformer-grade mineral oil used for arc quenching and insulation. It decomposes under arc to form gases that help extinguish the arc. 6. Bushings terminal insulators bring the conductors through the tank to outside connections. 3. Step-by-step, normal closing operation. 1. Control signal, local or remote, is given to close the breaker. 2. Operating mechanism drives the moving contact into the fixed contact, metal contact touches, current flows through the closed path. 3. Oil simply provides insulation around the live parts while the contacts are closed. No arc, so oil remains intact. 4. Step-by-step, interrupting a fault, opening sequence, the important sequence. 1. A protection relay senses overcurrent or a fault and sends a trip to the breaker's trip coil. 2. Trip coil actuates the operating mechanism to open the moving contact rapidly. The metal contact separates from the fixed contact. 3. Arc forms across the separating contacts, metal vaporized metal plus ionized oil gases. The arc current is very high initially. 4. The arc decomposes the oil near the arc into hydrogen and other gases. Rapid vaporization forms a gas bubble around the arc and changes local dielectric conditions. 5. Oil and the gas flow pattern, plus tank geometry, cools and stretches the arc. Insulation recovery occurs when the arc is cooled and its conducting channel is broken. The arc is extinguished at a current 0, AC, or when the interrupter can no longer sustain ionization. 6. After arc extinction, the dielectric strength of the oil and newly formed gases must recover so the gap can withstand system voltage. Once dielectric strength is sufficient, the breaker has successfully interrupted the fault. 5. Why oil helps? Short physics. Oil absorbs heat and produces gas that pushes the arc column apart and quenches ionization. Bulk oil gives both arc extinguishing mass and insulation volume so the live parts are well insulated from tank earth potential. 6. Maintenance and operational issues. What technicians watch for? Oil quality, carbonization, sludge and dissolved gases accumulate after interruption. Oil tests, dielectric strength, DGA, and filtration are required. Leakage and tank integrity. Large oil volume means risk of leaks and fire if not maintained. Contact wear and alignment checks after operations. Because of size and maintenance needs, BOCBs have largely been replaced by minimum oil, vacuum or SF breakers in many installations. 7. Advantages versus disadvantages. Quick list. Advantages. Good insulation and arc quenching capability for high voltages. Disadvantages. Large size and weight, bulky tank, higher cost, higher maintenance, risk of oil carbonization and fire. These reasons led to MOC, vacuum, and SF technologies supplanting BOCBs over time. 8. Short comparison, BOC versus MOC. BOCB, large oil volume used for arc quenching and insulation, dead tank. MOC, minimum oil interrupting chamber, uses only a small volume of oil, overall less oil, lower fire risk, smaller size, but different maintenance trade-offs.